Good evening, everyone. Today what we're going to talk about is finally what this section is about. Similarity. Yes, we're finally going to talk about what it means to be similar to something. It's going to be different than congruent, obviously, because it's a different word. But there are some, ironically, similarities between them. So, first things first, what is a similar polygon? Well, polygons that have all their corresponding angles being congruent, or congruent corresponding angles. They are similar. So, what it means is if all the angles match up from one polygon to another polygon, they're similar. Same exact shape. However, it could be a different size. So, for instance, I could have a shape like this, and a bigger shape on the outside, and if these had all the angles match up, what I would have is two polygons that are the same exact shape, but one is bigger than the other. So they're definitely not congruent, but you could say there is something similar about them. It's their shape. So we call these shapes similar because, well, they're similar. Same shape, but different size. If I ever wanted to say, for instance, like for this quadrilateral, ABDC, and this quadrilateral, EFHG, were similar, I could literally write it out this way. Quadrilateral ABDC is similar to quadrilateral EFHG. Or I could use this a tilde symbol. Just using the tilde symbol tells me is similar to. It's our mathematical term for is similar to. If we're talking about two shapes, that's what it means. Quadrilateral ABDC, a tilde, quadrilateral EFHG tells me those two quadrilaterals are the same exact shape, but different sizes. Yeah. 7. The corresponding parts. If it's similar, the corresponding angles have to be congruent, period. However, the corresponding sides don't have to be congruent, but they have to have the same ratio. Or you could say any pair of corresponding sides is proportional to any other pair of corresponding sides in a similar polygon. So, the same two quadrilaterals I had before. Angle A and angle E have to match up because they're the corresponding part of my two polygons. Angle B and angle F have to be congruent. Angle D and angle H have to be congruent. And last but not least, angle C and angle G have to be congruent because they're the corresponding angles. Similar polygons, corresponding angles are congruent. Now, length of segment AB and length of segment EF, definitely not the same size. It's wrong to say they're the same size. However, if I take the ratio of length of segment AB to length of segment EF, it's going to be the same as the ratio of BD to the ratio of FH. As it will be the same ratio of segment length CD to length of segment GH. That's what this part right here is in the bottom right. The corresponding sides, each ratio of the corresponding sides is going to be equal to any other ratio of the corresponding sides, as long as I'm going from the same polygon to the same other polygon. So for instance, if I'm going from the top polygon here to the bottom polygon, that ratio will always be the same. Now if I would go the opposite way, it's obviously going to reciprocate the ratio and most likely be different. Alright, by the way, if I set a statement that shows all the ratios of corresponding sides equal to each other, we call that a statement of proportionality. If I ever ask for it, what I'm asking to do is line up each corresponding side in a statement that shows how they are proportional. Alright, example 1. You know that quadrilateral QRST is similar to quadrilateral UVWX. List all pairs of congruent angles, write the ratios of the corresponding side lengths, and a statement of proportionality. Well, let me write this down. This is what I got. My two quadrilaterals being similar. If I talk about the angles, I know that every single pair of corresponding angles has to be congruent. The order matters. So angle Q here is going to be congruent to angle U, because it's the first angle. Angle R is going to be congruent to angle B, because it's the second letter. So those angles are corresponding. Angle S is going to be congruent to angle W, and angle T is going to be congruent to angle X. Because they are in the same corresponding location up here, they will be congruent angles because they're corresponding angles of similar polygons. Now the sides are a different matter. In this case, I know the sides aren't congruent, but I know the ratios of corresponding side lengths end up being congruent. So if I take the first two letters, length of segment QR, and I compare it to length of segment UV, this comparison will be the same ratio as if I took the middle two letters, length of segment RS, and compare it to the other two letters here, length of segment VW. That has to be the same ratio. I can keep going here. The last two letters, length of segment ST, will have to match up to length of segment WX. And last but not least, the outside letters, length of segment QT, would have to match up to length of segment UX. This is the statement of proportionality that shows the comparison of any two corresponding side lengths for my polygons that are similar. There I go. Both answers. I've written the statement of proportionality, and I've listed all congruent angles. Good job if you got it. Next thing. What if I asked you to verify that the two triangles are similar? Then write a similarity statement. How do I verify if they're similar? Well, two shapes that are similar have to have all the angles be the same, and all the sides have to be proportional. So that's a pretty simple check. I'm going to make sure that all the sides match up in the statement of proportionality, and I'm going to make sure that all the angles match up correspondingly. Alright, so this is what I have. Well, if I look at the angles first, angle A and angle D have the same exact measure. So I know that angle A and angle D are congruent because they have the same measure. Angle B and angle E are congruent. Same measure, 65 degrees. And last but not least, angle C and angle F are congruent. Again, same reason, but this time it's 55 degrees. All the angles match up. But that's not enough yet. I need to make sure that all the corresponding sides have the same ratio. So if I look here, A to B, to D to E, has to be the same as B to C, as it is to E to F. And last but not least, A to C has to have the same length as D to F. Again, these are the corresponding locations that match up correspondingly. Well, let's check to see if that statement of proportionality is true. Length of segment AB is 5. Length of segment DE is 10. Length of segment BC is 6. Length of segment EF is 12. Length of segment AC is 7. Length of segment DF is 14. Simplify each ratio independently. So right now, I'm going to ignore this equal sign, and I'm going to put a question mark here, because I'm not sure if they equal each other yet. I'm going to find out though. Well, 5 over 10, well, both are divisible by 5, so I get 1/2. 6 to 12, well, I want to get 1 on the top, so let's try dividing the top and bottom by 6. Well, I get 1 to 2. Last one, I'm trying to get 1 on top, so I'm going to divide top and bottom by 7. 1 to 2. They do in fact equal. This was the last check These triangles are similar. I now need to write the correct similarity statement. So if I'm very careful here, triangle ABC. If I went ABC, correspondingly I would have to go DEF. The order matters. And there we go. I have now verified that these two triangles are similar, that they're the same shape, different size, and I have given you the similarity statement. We're done with the big part of this section. At this point, what we're going to talk about is what we call the scale of similar polygons. It's really not that hard. It's really not that bad. The scale factor is the ratio of corresponding sides of corresponding triangles or corresponding polygons is called the scale factor of the polygon. So if I would look at this one back here, the scale factor would have been 5 to 10 or 1/2 because the ratio of the corresponding sides in this case was 1 to 2. This triangle to this triangle, scale factor of 1 to 2. Two corresponding sides, that's the ratio. In the picture on the PowerPoint here, I see that side AC and side EG look to be corresponding. In fact, if I look at the similarity statement down here of these two polygons, I have AC and EG to match up to be corresponding locations. So, if they're corresponding locations, and I know those polygons are similar, their scale factor is 5 to 10, or again, 1 to 2. So all I'm doing is saying, what is the ratio of their corresponding sides? If I ask for the scale factor, I'm saying, what is the ratio of their corresponding sides? It's a pretty easy question. Alright, so in this case, they're asking me to determine the scale factor of these two triangles. So what it didn't say is these two triangles are similar. I really should have said it, but these two triangles are similar. Trust me on this one. I know the ratio, I don't know the ratio of the sides yet, but that's all it's asking me to do. It wants the scale factor of the ratio of the sides from triangle DEF to triangle GHI. Remember, order matters here. So if I'm going to compare this triangle to this one, I choose one from this side first. Now, if I look at triangle DEF, only one of them is a whole number. And that's this length right here. That's the first two letters. So if I was going to compare these two, I'm probably going to choose 6 here, and I'm going to compare it to, well, DE matches up to GH, which is 5. Can I simplify 6 to 5? Well, 5 is prime, and 5 doesn't go evenly into 6. Leave it at this. The scale factor of this triangle to this triangle is 6 to 5. You should have gotten the same ratio if you would have done the other two. However, I'm not going to go into that just yet. Example 4. Sorry, not example 4. There's two last concepts I really need to talk about. It's this thing about scale factor. What we noticed is, hey, it's not just the ratio of corresponding sides. It also matches up for the perimeters. The scale factor is the same ratio as the perimeters will be. So in this case up here, I said 6 to 5, right? Well, if I would have taken the perimeter of this left triangle, I would have gotten 18. If I would have taken the perimeter of the right triangle, I would have gotten 21.6. Now, I said the scale factor of this polygon was 6 to 5. Well, that's true. Now, the ratio of their perimeters should be the same exact ratio if this theorem is right. So, let's check it out. Does 21.6, is it the same ratio as 18? Well, how can I verify this? Cross multiply. If I cross multiply here, I should get something that's true. If I get something that's wrong, I did something wrong. 5 times 21.6 is 0.0. Good. There's an 8 here. Good. And there's 108. 6 times 18 also ends up being 108. I get 108 to equal 108. The ratio of their perimeters, 21.6 to 18, is the same as the scale factor of these two polygons. It's true no matter what polygons I'm talking about. It can be quadrilaterals, pentagons. If they're similar, their perimeters are the same ratio or proportional. In fact, the ratio of any corresponding lengths in two similar polygons is equal to the ratio of their corresponding side lengths or scale factor. So, if I look at the picture here on my PowerPoint, I am told that triangle ABC is similar to triangle DEF. Well, if I look at these sides here, it's a 2 to 4 ratio. 2 to 4. That means this length here from A, I didn't put a point down here, but this segment here, the median, because it goes from the vertex to the midpoint, is 3. This median goes from D to the midpoint and it's X. This would have to have the same exact ratio because they're corresponding lengths of similar polygons. Any corresponding lengths will have the same ratio as the scale factor or the same ratio as corresponding sides. Whoa. If you're looking for any length of similar polygons and you know the scale factor, you should be able to find them. Well, let's apply this idea. In this example, I tell you that my two pentagons are, in fact, similar. Pentagon ABCDE is similar to pentagon FGHJK. No joke. And what else I know is, well, they don't tell me anything else besides what's actually drawn in the diagram. But they want me to find the scale factor, and then they want me to find the perimeter. Alright, so they tell me these two pentagons are similar. They want me to find the scale factor. Well, to find the scale factor, I need to match up two corresponding sides. I also have to tell you which way I'm doing this. So if I'm doing pentagon ABCDE to pentagon FGHJK, I have to write that. The scale factor, well, here is corresponding side to here. So 12 to 15 is the scale factor, or better is 4 to 5, because they're both divisible by 3. So the scale factor from pentagon ABCDE to pentagon FGHJK is 4 to 5. Next question. What's the perimeter of this pentagon? Well, I could do this 4 times and figure out what each of these lengths are by using corresponding sides have to have the same ratio. Or I could just find the perimeter here and compare it to my scale factor. So the perimeter here, well, that's 15 plus 9 plus 12 plus 15 plus 18. If done very carefully, you should get 69. Well, the comparison went from that to this one over here. I don't know this one, so I'm going to label it as X temporarily. X to 69 has to be the same as the scale factor, 4 to 5. At this point, cross multiply and solve. 5x equals, let's see, 4 times 69, 36, 276. Divide both sides by 5, I get 5 and 5.2. Although I really should say this is perimeter of my pentagon ABCDE. So, scale factor, I found the perimeter. The perimeters are the same as the scale factor, and the scale factor is the ratio of corresponding sides. Just make sure you label them properly, and if you're going from the right to the left, make sure you're doing it correctly. The last example that I have is because I said any corresponding lengths match up to the scale factor. Well, what if I gave you an extremely weird shape? Alright, I give you all this information, And I'm looking for the length of this segment, altitude CF. Well, the first thing I might do is find the scale factor of this shape. Well, it just so happens I have this and this side, BC and CE. I have those two corresponding lengths. So why don't I compare, well, the left triangle to the right triangle. So 18 to 24, or my scale factor when reduced is 3 to 4. So this is the scale factor of my polygon. I guess I really don't need to box this here. However, it is an important number to use. Well, I'm looking for this length here, x. I put it on top because it's my left triangle. Its corresponding length is the altitude in the right triangle, which happens to be 20. My scale factor of 3 to 4 should be the same ratio as altitude in my first triangle to the altitude in my second. Any corresponding lengths equal the scale factor. And the scale factor is just a ratio of two corresponding sides. I have two ratios that are the same. If they're the same, set them equal, solve for x. Cross multiply. 4x equals 60. Divide both sides by 4. X equals 15. And I wasn't looking for f, I was looking for the length of segment CF. So I am going to change my answer just slightly, but there I go. And I'm done. So the big new thing here in this section is, hey, triangles and polygons can be similar. If they're similar, corresponding angles are congruent, sides are proportional. Corresponding sides are proportional. It also happens that the corresponding sides, corresponding altitudes, corresponding medians, corresponding perimeters end up being congruent also. Any corresponding length will be the same ratio as any other corresponding length in similar shapes. And that's all I have for you today. Until next time.